I didn't really know what I was doing today. I was supposed to show up here and just talk about science, and then I realized that maybe I should give you a little more background and stuff. So this will be a little bit technical, but one thing I wanted to point out is part of my research project is to develop materials for K through 12 education. And this is a federally NSF-funded grant, NSF Career Award that funded this work, and I'll show you all the details and stuff that we do here at San Jose State. But the outcome of it is to have new knowledge and have that new knowledge put into the school system. Basically, and I'm not aware of the new science standards in the state that changed when I had already gotten funded, so I totally don't know what I'm doing. But San Jose State has a education program in the College of Science that bring teachers in and help faculty like myself develop materials. So we're building a material, or a set of lesson plans for wildfires, it's pretty important in our state, that ties into like thermodynamics and heat transfer mechanisms. So I kind of tailored it towards 6th grade, but it sounds like a lot of people here are high school science teachers, which makes me nervous because if my high school science teacher knew that I was doing this now, they wouldn't believe, they would not recognize me. They'd say, no, that's not right. So, because I was not college bound, believe it or not, in high school. I grew up in the Bay Area, with San Ramon High, with the DVC, then did my education out of the state. Went to many different universities, dropped out of one, finished a PhD in Houston, and then got a faculty job at San Jose State, which was my dream job, so it all turned out. But it was a long road. And, Calculus 1 almost made me quit college. So that's what I tell students every time, because meteorology is a pretty tough major in mathematics, and everybody wants to be, well, not everybody, we get like 10 majors out of the 5,000 engineering students that come to San Jose State, so we're always having to justify our program at state. And we get those 10 majors. Oh, do you like math? No, okay, well, let's see how it goes. And our attrition rate is 50% per semester. Calculus 1. Nope, I'm going to do something else. There is a big problem in STEM, as you know, and this is something that we are all trying to deal with. And I know probably at your side, and then they come to us at our side. So, anyways, I'm going to talk about wildfire research today. And like I said, these materials will be available, and I'm developing materials for, you might have missed it, for middle school, science, and high school. So those will be coming. So I'm going to talk about fire weather and fire behavior basics. And then I'm going to talk about what I do and what we do at San Jose State. And then I'll talk about this education program for middle schools. And it can be applied to high schools too. So, oh, this is too technical. So basically, the idea of my research is to better understand how weather affects wildfires and how wildfires create their own weather. And you see this sensationalized in the media just the other day, and it really makes me angry. I was on the news yesterday a couple times, and I turned down CBS 5 today just because it's the same old, same old. It's just crazy, but whatever. So this is my research, is to better understand how the atmosphere and wildfires interact, and what drives wildfire propagation. What you've been hearing is climate is driving, you hear the governor. I'm glad that it's gone. It's all climate change related. Yes. But those 400 homes in South Lake on Saturday, they were burned because the winds were 25 miles an hour. And we're writing analysis, but our colleagues across the bay at another university said something sensational, and it went to the New York Times, and it's completely wrong, and it happens all the time. Okay, so Smokey says, high fire danger. You've seen this, it's always high. This is California. So fire danger is always high in California, basically. And so, what is fire weather? This is the first question I asked. I teach a course in fire weather at San Jose State. We're the only program in the U.S. that focuses on fire weather, actually. And it's our extreme weather. We don't have tornadoes here or hurricanes, so we have to do something to interest students because it's boring weather, right? So I tell students why the rent's so high here. It's beautiful. Anyways. So it's hot, dry, windy. These are the conditions that we have basically from May through October. always hot, dry, and windy. It's particularly dry and windy, or particularly dry when the winds come from the north, called a north wind. Sometimes you may have heard it as a Diablo wind. That was the Oakland fires in '93. That was a north wind, very dry. It's impressive. So there's AMS glossary of the American Meteorological Society. Fire weather variables, especially wind, temperature, humidity, relative humidity, and precip that influence fire starts, fire behavior, and fire suppression. So this is kind of what we study. This is what we try to forecast. Believe it or not, this is, most people are trying to forecast tornadoes and thunderstorms. Here we're trying to figure out what the humidity is and what the wind is going to be at very fine scales. Okay, so fire behavior, you hear a lot about fire behavior in the media. Fire behavior is how the fire moves. How tall are the flames? I didn't put those slides up, and I can make them available, but do the flames tilt over, how fast they spreading, how much heat is being given off by the fire, and that's what we call fire behavior. And what drives fire behavior is weather, topography, and the fuels. Fuels are grass, shrubs, and trees. And so there's an article just published, and I know Scott Stevens at Berkeley is a big fire researcher. We collaborate once in a while, and he was quoted talking about the bark beetle infestation due to climate change in some of the pine trees in the coastal mountains just in Napa County. So what happens is, another reason why that fire behavior was so severe on the Valley Fire was really weather driven. But the fuels, if you look, and I was going to show this today, you look at the fuels, and we talk about the brush. We sampled the brush in Los Gatos, and there's a fuel site, I think, in the east side. It's actually very far east. It's in, past Henrico State Park. We go out and clip the brush, weigh it, dry it, reweigh it, and we get the fuel moisture content. So fuel moisture content is a big factor. What's going on with the drought, it's not the grass, it's not the brush. Those fuel moistures are the same as they were last year or the year before, and they're in the climatological norm. But everybody's talking, oh, it's the drought. The drought is killing the trees, and the trees are fueling bigger fires. So the forests in the Sierra are definitely a drought problem. But if you don't have the wind, well, if you don't have people making mistakes and fires, but you can still have light. Remember 2008 here in California, we had 3,000 ignitions in a day because thunderstorms rolled through. We don't get a lot of it. So anyways, I'm biased, I'm a meteorologist. I had to take all the math and physics. My friends who are biologists, they do fuels, they get to go out and play with plants and stuff. They don't have to do anything. This is an experiment. I'm going to talk about different fire types. Fire experiments are, this is what I did for my PhD work. This is actually in Houston, and this is like, nobody had done this before. That's how I got involved with this. It was a dumb idea. And I remember when I took this picture, I thought, I've been waiting tables for 10 years, and I'll probably get fired from the university, and I will never get my PhD. It's not going to happen. But it turned out, when this fire went through this tower that I had set up, this is a 150-foot tower with measurements on it, and I'll show you some more examples. We collected data that nobody on planet Earth has collected before. And it turned out that this was the first data set that wildfire behavior modelers, people that model fire behavior, could use to then test the models. So we know, we can forecast the weather pretty good, right? I mean, you pull out your iPhone, it's like, oh, it's going to be cool in the morning and sunny in the afternoon and high of 80. So you know what to wear. Fire, we do not have that app. We do not know how, we know how it spreads, but it's very hard to forecast. So this data set is kind of how I got involved, and I'm going to talk a lot about experimental fires and then actually studying wildfires. So these fire experiments are, we set fires on purpose to study them. So those are experimental fires. Prescribed fire is something that is done, and this is not done in California enough, but it's fire set for land management. Generally, the forests in the U.S., this is going to be published online. Forests in the U.S. are well managed by the federal government, but what happened is, 100 years ago, the Forest Service developed this idea that we have to suppress all wildfire. And so we have an accumulation of fuels. When naturally lightning would strike and the forest would burn out, but it wouldn't burn hot and it wouldn't burn the trees. And we call that stand placed in fires. So like if you look at the fires in California right now, you just barely see toothpicks where there was big trees. That's called stand replacement. It's burning the whole canopy. It's burning the whole vegetation. When naturally that fire should burn underneath, have scorch marks about this tall, no big deal. The trees can handle it, and it burns through, and it clears up the brush, and that is beautiful for a forest. A forest that is well managed is a beautiful thing. You walk through, and Yosemite National Park actually uses prescribed fire to manage the forest, which is really interesting. You can see some areas that are just beautiful.
Which places?
Yeah.
What part? Yosemite Valley. Yeah. Actually,
Well,
they did.
if you go through Big Basin, you're going to see redwood trees that are fire
Yeah.
scarred,
Yeah.
and they're still living.
Yeah.
That was a natural part of the environment.
Yeah. There's,
Can I just
yeah.
say one thing? Because I'm dying to say, Sierra Pacific, the #1 logging company in the U.S. is logging the dead forest in the fire, in the rim of fire.
In the
This fire,
Yeah.
I'm very scared. What is the cause? Why is it totally no control? After it's burned, someone can go in and log all the trees.
Well, the Forest Service suppress fire to keep the trees. I mean, it's a resource. Whoops.
Yes.
So there's a lot of politics and a lot of management issues that I can't speak on professionally.
I know.
On
Because I spent a week in
That's right.
forest.
At least I've tenured.
Okay. I'm totally tenured.
Yeah, but no, but I'm just saying that like this is a whole discussion that we can have off camera. Wildfire that requires control. There's a lot of politics on fire.
No, I bet there is.
Yes.
And obviously stories about my research. Okay, primary factors affect rate of spread of wildfires. Wind speed, steepness, slope, and changes in fuel. So, really windy, real fast fire spread. So there's some materials here that can be used for teaching at this level. There's lots of materials at this level for that we're working on as well. This is actually firefighter training materials. This is the standard S290 or S190 firefighter training. So fire spread and area growth. So here's an ignition point, and this is your typical kind of parabolic shaped fire. It spreads, if the wind is blowing this way from left to right, the fire is pushed with the wind. But you notice that it does spread back, so it's called backing fire. This is called the flank. This is called the head. The head is the hottest, most dangerous part. Flanks are not that, I mean, they're dangerous as well, but the backing fire is usually, they don't even worry about it. Generally, they try to attack, suppress the flank. You would never get a crew or engines in front of this region here. It's just too hot. Flames could be 100 feet tall. So it depends on the fuel type. If it's a forest, your people are running. That's what you saw on the news on Saturday, the Valley Fire. Okay, so here's something that's pretty neat. So why do we need this data? Well, I showed you the picture of that tower with the fire in front of it. This is a simulation with a French weather model. And these are my colleagues in France. And they got hold of my data, and we worked on it together. I gave them the data, and there's the fire. And what you're seeing here, okay, here's the fire front. These are wind vectors. They're simulated. So this is a 3D computer simulation with the fine scale, like this is France's top weather model linked to France's top fire behavior model. And what you're seeing here is just turbulence and smoke as a tracer. Don't worry about these lines. These are short of kinetic energy lines. Don't worry about that. But we can simulate pretty well the atmospheric conditions around fire. And so what my team at San Jose State does, and my whole research program, is to generate actual data that can be used to validate or evaluate these model simulations. So we go out with all sorts of instruments and set up towers and do these experiments. And actually, this was our experiment from 2006 that they simulated. So this is the state of the science of fire behavior modeling. Now, if you're what's called an FBAN, or a fire behavior analyst on one of these fires in Northern California, incident management team right now, You don't have access to this. It's a supercomputer that's running this model. It takes a long time to set up. And so the modeling tools are very simple. But we're trying to move to that new stage, that new state. Yes?
I just have a kind of strange, things coming up on that video. Is the smoke holding the fire, or is the smoke the end result of the fire?
That's a good question. So what you're seeing is the smoke. Once you combust, you're giving off combustion products and smoke. Smoke is being pushed by the wind. And so that's why it's leading downwind. And we call this a tilted plume. So the plume is tilted over. Because that has an effect on the atmosphere ahead of the fire, and we do not know how that affects the fire front. We think it actually helps drive a low pressure system ahead of the fire line that actually I'm going to show you a little bit of in just a bit. So here's an actual fire that we did in 2013 as a follow-up to the first experiment, follow-up to those simulations. And we went all out, all sorts of instruments, I'll show you that, but this aircraft here, or we're about, I think this helicopter's a couple thousand feet. And there's a lot of politics on this day, because this is in Galveston County, outside Houston. Before I even woke up, the news crews on TV were saying there's some people from California in Texas that are going to do a fire. It was a red flag day, which means burn down. And so this, I don't know how we did this, but we had a bunch of people show up, a lot of scientists. I probably spent $200,000 of your tax money, helicopters in the air, and they said, you can't burn. I said, no way, we got to do this. So we got it. And it was crazy because it was too windy to do it. But this is the first experiment on planet Earth, probably besides Australia. Australia didn't do anything yet. And so, first experiment the idea was to burn it from here all the way down, but we couldn't get the wind in 30 days. And my students out there flying back and forth, California and Texas, they had one day with the perfect conditions, and it turned out that our colleague at the National Weather Service issued a fire ban. And it was the perfect conditions. We had red flag warning, we've got the conditions. So that's a grass fire. I don't want to go spend a lot of time, so this was the original plan with the experimental setup. Here's a simulation, just like that other model, but this is an American model, Warp S Fire. My colleague did that, so we actually ended up moving everything from this grid to this grid. It's a lot of field work. I'll show you how and why. So let me just click all this. Lots of instrumentation towers, pressure sensors, anemometers, sampled the fuels, which was National Forest Service, their team, air quality, this thing called the Doppler LiDAR, which I'll talk about in much more detail in just a few more slides. That scans like a radar, or uses a laser and scans across the field, gives us winds. And so this is the most instrumented fire plot in history. And I still have students working on the data. Just a close-up of what you're looking at. Remember the first tower I showed you? The same tower. Here it is. This is actually Dice. He's now doing his PhD in New Zealand, but he is my research graduate student. And so we set this tower up. Well, the tower's fixed. But we have all sorts of instrumentation, custom sensors by the U.S. Forest Service. These are sensors that we use constantly or throughout all our burns. And we wrap the base of the tower with this material. This material is fire shelter material that firefighters take to the fire line. They have a little pack. And when worst comes to worst, they have to pull that out. It's a bag. And you get down on the ground. And the whole team is also trained in that technique, because it's the only thing that you can possibly survive a fire, and a lot of times it doesn't work. But anyway, so the SGSU researcher to give you scale. So we set up a lot of equipment to do this, and this is the cool stuff. This is why GoPro is so great. Let's just get to it. There's sound.
It's up on the tower during the day.
It's just wind. Okay. You see that?
That's quite a bit of wind.
Oh, it's very windy.
Yeah.
Blowing about, let's see, meters per second, 7, so about gusting 18, 20 miles an hour. Kind of like what happens.
You got the, what is that stuff? The mesquite. Texas got mesquite, right?
Yeah, but this is actually Chinese tallow.
Oh, it is? Okay.
There's a sensor here, a camera here, there's cameras here and sensor packages. We have sensors all around the tower. Yeah, and so synchronized videos. It's pretty fast. It burned from here to here in 3 minutes. So it's like $200,000, 3 minutes done. But we'll probably get 5 to 8 years of research papers out of this data set. So this is a view of top of the fire. Nobody's seen this before. Actually, a colleague of mine, Mark City at the U.S. Forest Service, top fire behavior modelers and researchers that have never seen this view like that. And there's lots of work going on what's causing the fire to propagate forward, different theories and stuff. Basically, it's wind, it's hot, it's pushing the fire, but there's a little more physics involved. I don't want to bore you with some details, but this is the temperature structure measured from the tower. Obviously, it's hot near the fire, about 350 degrees. So we're not actually measuring this is not flame temperature, this is just heated parcels of air that impact the tower from the flame front. And so my theory of how this grass fire spreads is we have ignition temperature air being affected or pushed by the wind, touches the plants, moves forward. My colleague in Europe, he looks at it a different way, thinks it's all radiation. So there's different ways that we think fire spreads, but it's all about the same.
That's the height.
Yeah, it's basically 40 meters here. So the warmest, highest temperatures are real close to the ground, as you expect. But what happens is because of the wind, there's lots of entrainment. So that's why you think, wow, this big, huge smoke column has got to be thousands of degrees, and there's probably only 100. Right? It's not that hot because so much air from the ambient atmosphere is entrained, and that's something we're trying to calculate with some of our wildfire measurements. This is the wind structure, so very strong winds. Can't really see the scale, but looking at about 8 meters per second. And what you're seeing, you're not getting a big shift in the wind direction. There's a little bit of a wind shift that's moving, well, this is looking down. So what these vectors mean is if you're looking at a compass, you're looking straight down. So this would be a wind blowing from the northwest. Okay, and they kind of shift slightly more westerly. They weaken a little bit, and then they are strong here, and at different heights. So that's kind of a weird plot, but it gives us an idea of how we can measure all this data near the fire. Okay, so I want to move on to the really cool stuff. Wildfires. So we've done the experimental fires, which we still find very useful, and we still use these experimental fires because we have complete control. Believe it or not, we can set up all the equipment, and we let the fire go, and we know where it's going to go, and we know what we're going to measure, and we have redundancies, so if something melts, which it does all the time, we have replacements or we have multiple measurements. So here, this part of the campaign is what we call Rapid Deployment to Wildfires campaign, or RADFire. And we take our truck-mounted instruments that's parked at San Jose State, it's funded by the National Science Foundation. We're all Fireline qualified, and I take students and myself to wildfires, and we get really cool data. So here's the truck. It's called the California State University Mobile Atmospheric Profiling System. It's about $1 million facility. There's other instruments that are not shown here because there's a trailer involved and all sorts of things that share with San Francisco State. But right here we have, we can launch weather balloons, we have a weather station, we have Wi-Fi comms, we transfer our data in real time to our website, and then we have what's called a Doppler LiDAR. It's a laser radar. It's just like a weather radar, but it uses a laser. And then this is another temperature profiler. So we're highly mobile, and we can roll and go to a fire. And we went to, let me show you a little bit about the laser first. I'll show you a lot of data about this. What it does is it's like a radar, it shoots this infrared light into the sky. We can point it anywhere because it's got a rotating head, which is like a radar. We do all sorts of scans. What it does is it gives us aerosol backscatter, so particles in the atmosphere scatter the light back to the LiDAR. And so what you see here is this is like smoke and aerosol. This is just up in San Jose, so this is just aerosol in the Bay Area. It's pointed vertically. We can know the top of the what we call a boundary layer, the convective boundary layer, where motions are convected. So like if a sea breeze blows in the afternoon, which it always does in San Jose, this would become lower. At the same time, we can measure velocities. So these are updrafts are red, downdrafts are blue. So we see where, if there was a cloud passing by, we'd hit the cloud, but we'd see the updraft into the base of the cloud, and we'd be able to measure the downdraft around the cloud. So we can scan all around and do all sorts of crazy stuff. It's mounted on a truck with an airbag frame system. So, yeah.
Is that showing an inversion, or can you see an inversion?
Yeah, well, no, actually we different ways, but inversions are generally measured by temperature. And so we usually use a weather balloon to do that.
But usually when you have an inversion here, you have to put the
You're right. So this, I don't know what this is, but this would be technically the top of an inversion. And this could be actually another inversion here where it's a little cleaner air. But yeah, we can actually map the top of the inversion. Okay, so 2014 we went to 8 fires around the state, and we got a lot of cool data. One thing I want to show you, just some examples here. Here's just a plume that's converging. So air is moving into the fire. Compared to the plume on the other side, which is just a few minutes later. Full rotation. And so this is great. I mean, not if you're a firefighter in there. We do not want to see this, but meteorologically it's very interesting, and we're able to actually slice through this with the LiDAR. And so this, if you've heard of fire whirls or fire tornadoes, you know, we try to capture a lot of this. It's an extreme fire behavior characteristic. It basically is like a tornado but made of flame, and it can transport fire real quickly to different locations. And it happens very suddenly. And so with this LiDAR, we can actually, so reds are away, just like before, and blues are towards, and we can scan and detect these areas that we call wind shear or wind shear couplets, just little couplets of wind here. So you can see the circulation. Reds are away from the LiDAR, blues are towards, and the maximum's here and maximum's there. We actually see cleaner air. This is the aerosol, so this is like the smoke particles. We actually see cleaner air being entrained into that circulation. And if we track it, the LiDAR's here, this terrain, the dots are just helping us visualize the top of the terrain. You can see that circulation, the reds and blues, and they're close together right here, right there, moving and evolving around the mountain crest. See how it kind of drops down and moves up. So it's interacting with the topography. So these are pretty cool stuff that we get to study with this tool. And it's state-of-the science, and you can bring it to a school near you. Seriously, I mean, I want to bring it to your school.
Are you funded by National Science Foundation?
Yes.
What do they use the data for? To
Well,
prevent
they
fire?
We use the data, they just give us the money to use to collect the data and do our science. So the National Science Foundation funds our project. We basically write a proposal, it gets reviewed, the National Science Foundation then takes the proposals and looks at it and says, okay, we can fund you, and then they transfer the money, and then I get to hire students, staff, and buy equipment, and then run the project. And then in return, I publish the results, and I give NSF credit in the acknowledgments with the grant number. I also make the data publicly available to anybody, as part of NSF's policy. In this project particularly, I'm creating education materials for schools. So hopefully I can get that sooner than later. Real quick, I'll show you a couple
Why
movies.
did the federal government not use the data to do something about fire prevention?
Well, that's the idea. I mean, my colleagues, that's U.S. Forest Service, National Science Foundation, they just fund science,
No.
which is fine.
Forestry did not do anything with this data.
Well, actually none of this data has been published yet, so some of it has. This is fresh. So yeah, hopefully we can get what we're doing with this data as scientists and my team, as we're working with other groups. What I want to show you is look how this plume just punches through this inversion here. Right there, and watch it keep training down like that. So the smoke comes back down and it rides on top of the inversion layer. I showed this to the LiDAR manufacturers. LiDARs aren't cheap. They range in cost from $300,000 to $700,000. I mean, this is like a very expensive instrument. And I had a LiDAR manufacturer from another company show up. As soon as they stayed to like, hey, you know, we showed them this. Couldn't believe it. So I can't believe you're getting that type of data from a LiDAR system. And neither can we. I'll skip this. It just kind of shows where inversions are and the temperature. So this red line is temperature, potential temperature. Don't worry about that. And that's a little inversion. Smoke gets trapped in each of those inversions, just like air pollution here in the Bay Area. Here's the El Portal fire in Yosemite. These are my two students. This fire is burning in a clump of big stand of trees, and you can see the plume. what was unique about this, and we're working on a research paper just on this one plume, is we were able to scan it for a couple hours. Usually the fire's moving and moving, and we can't, this thing just kept burning in pretty much the same location. So we're able to get a long-term, hour or so of data, and we can get statistics out of it. So let me show you this movie. And I like to use the photo because the LiDAR is like an X-ray of the smoke plume. And we just drew this contour in a mountain. And you'll see some of the terrain. But look at the structure. We're seeing all these little lobes and little circulations and just constantly. And what's going on is the truck is parked and the LiDAR is just doing this for a couple hours. And we were able to launch a weather balloon, so we now have the atmospheric conditions around this fire. I mean, we can say a lot about the plume. It's the first time these have been measured like this, believe it or not. So this is San Jose State right here, measuring the state of the science. Keep telling the university that they got a lot of fun to us. So we get mean properties of the plume, statistics and stuff. And this is a cool plot here. So what this is just a snapshot of this time. It's one sector scan. Here's the smoke contour. Okay, look at the clean air getting in there. So the dark colors, obviously higher smoke concentration, light colors, more cleaner air. But what you're seeing here are the blues and the reds. So the LiDAR is down here and it's doing the scan like this. So blues are towards, reds are away. So we have this area conversion that's going to the plume. We also have circulations like this, circulations like this. So we're able to actually measure the circulations inside a fire plume and around the fire.
Do those circulations correspond to where the inversions are?
Not necessarily, no. These actually, the inversion here, there's one way up here and down real low. These are actually just these little bubbles, we call these little turrets. Convection cells. And so that's what we're able to detect. So, okay, so the thing's doing its thing, the plume's doing that, why do we care? Well, we need to have this data so we can model the plume. What happens on a lot of big fires is we get this phenomenon called plume collapse. And that's when the plume goes up and somehow comes back down, either as very cold air because it's cooled, maybe we had some evaporation, there may have been liquid water in there, and we get air coming down. And that's a dangerous situation for firefighters. So understanding just these kind of plume structures is important. Why is it dangerous? Because let's say, for example, you've got this fire here, the winds are basically blowing here, we get a fire-induced wind where it's coming back in here, but
Just so you can turn back on.
yeah, if you get air that's rushing down, it rolls back down. And that happened in the Dude Fire in 1990, I believe it was, in Arizona, or 19, well, firefighters lost their lives, or it was 11. And then, remember the Yarnell fire a couple years ago, 19 firefighters lost their lives. That was a storm outflow boundary as well.
But when it returns, right, a lot of the fuel's already burned, right?
Yes, in theory. Yeah.
In theory.
So sometimes it might have burned low intensity in that area. It'll come back and maybe burn fuels that did not get ignited. Or it may go this way and they're on this side where the fuels are.
Okay.
So it's a watch out situation for firefighters. Let's see here. Yeah, so real quick, this is the average velocity. So look at the velocity. So again, reds and yellows are this way, blues are this way. And so you can just see that average in the flow. Alright, okay, one last topic. So when we were out on a fire in Northern California, we came across this phenomenon that we didn't understand it. And it was by accident. We just published this paper in one of our top journals, Atmospheric Chemistry and Physics. And what it is, it's smoke-induced density current. So a density current is something that's, like our sea breeze here is density current. It's cold air. And so it flows into areas that are low pressure or warmer. So that cold air rushes in. That's why San Jose is perfect weather. It's always cool in the afternoon. It never gets that hot because we have a cold ocean and it flows down through the gap in San Francisco Bay. It comes down and then that cold air.
Unless you have offshore wind.
Unless you have an offshore wind, yes. So that's a density current. It's just like a cold air layer that moves. Turns out that you can see this thing. It's actually moving away from this huge wildfire that's over here. The winds are this way. And so if you were to forecast the smoke, which on every wildfire incident in the U.S., generally, major wildfire incident, there are smoke forecasts. Because smoke, you don't want to be breathing a lot of wildfire smoke. It's not good for you. So the federal government, the Forest Service, issues smoke forecasts. Well, smoke models do not take this phenomenon into consideration. We didn't know it existed. It's been hypothesized. And some observations in the 80s showed that a big plume of smoke came over, I think it was Baltimore somewhere, and the temperature went down. That's just because it's like a cloud that shades. So it's smoke shading. And what we discovered is that near wildfires, this density current, or this smoke layer, can propagate as a density current. And what happened is we were driving out to go study big wildfire plumes with the LiDAR. We were going to do those scans that I was just showing you. That was our goal. And it was like really smoky, and we drove through and it cleared up. And my colleague, Dr. Leroux, he's a postdoc working with me, he said, "Oh my gosh, look at this." And he looks at the computer, because the thing's running. We run it on the truck. We just drive across the state and we're collecting data. And so he said, "It looks like a density current." I'm like, "Oh my gosh." Turned around. Drove back through it. Turned around. Drove back through it. And then we parked and did some special types of scans where we were able to let this thing come at us. I mean, it's just smoke. Right? It's not like it's on fire. I mean, it's just a layer of smoke. It's like one of those scary movies like this on TV. It's like, oh, it's the mist. And so it's like a smoke layer. It came over, and we launched a weather balloon through it. We were able to document this thing by accident, and we just got it published. And like, people, it's crazy. We tried to submit this to a top journal. People were very interested. We presented at a conference. Everyone said, "You got to present that. You got to submit that to Science or Nature." Like, oh, we tried. So we went to the next one. So what happened? This is Cat Creek Valley up near Lassen. There was the Eiler fire and the wildfire. And we had sampled the wildfire the day before. That was the picture on my first slide, that big pyrocumulus cloud. And we were driving this road, and it was very smoky in here. And we drove out. That was our intercept A. And we drove along the road, then we turned around, came back, and we drove around, and then we came back and kept trying to chase it. And satellite images show where that smoke is initially relative to the map. So there's the outlines of the two fires. You can see, from just satellite imagery, enhanced visible, it propagated. The winds are this way, though. How's that smoke moving that way? So that's very interesting meteorologically. So that's what the smoke did. And here's what the scans look like. And I don't want to go into too many details here, but the blue dots are temperature from the truck, because we have a weather station on the truck. And it's like 3 degrees Kelvin difference than the ambient. Okay, so 30, it's like almost 4 degrees. That's a big temperature difference between just being in a smoky area and where it's not smoky. And so that's enough to drive the circulation. And it has this crazy little head here, it's classic. These images look like what you would see in a 1960s fluid take experiment from the literature. It looks just like this. I cut those slides out because I didn't want to bore you to death. But so this is this structure of this flow, smoke-induced density current. It's brand new science. It's a very big discovery. And it turned out, once we presented this at some online presentations for firefighters and fire managers, we got some calls of some were saying, "Hey, we think there's a density current incident on this fire." And so now we're on the lookout for them. And that's that. That's what it kind of looks like. This is what we were in, and we drove through it. And it's like you wouldn't think. You just go, "Oh, it's clear now." But it turns out the things we propagate. Got a little summary here, but I won't bore you with those details. What I do want to talk about is what I'm doing in part of this education program, teacher training program. So we're doing it. Oh, I've got a logo that kind of got out of control there. The one-day workshop at SJSU. This was tailored for 6th grade science needs, but maybe we can, I need to go back and think about what I need to do between the two. Yes?
So with the new NSS, they're kind of integrating the earth science as part of the rest of junior high, so that's good for
school or no?
Yes,
Well,
high
yes.
school.
Middle school and
Integrated
high school.
science model for 2 or 3 years with earth science.
Oh, great, so I can get both levels. Okay,
Yes,
good.
please.
Everyone is doing her.
Everybody's just
Everybody.
panicking.
Okay, good, because that's,
And others know very much about it.
well, I'm biased, but I believe that wildfire science should be in the curriculum in the state of California. And why not? And I'm funded to make it happen. It's just something I've been kind of like, oh, I gotta do this, how do I work with teachers? And there's a whole group on San Jose State Science Education where they build these workshops, they help us build these materials.
High school one.
Okay,
Yeah, we do. And if there's any way to convince the
Yes,
school
I would be-
system
I would go.
to actually make it a lab science in high school, then I'd be much happier as the earth science teacher who can't get it to be approved.
so what do I need to do? I'll give you my information.
I'll talk
This
to you later.
this is the plan. So this summer,
Light on fire.
yeah. And so I want to provide materials and resources, like images
Email.
and contact. Yeah, no, I've got all my contact information. And then also, outreach program for middle schools. We had this thing, or high schools. I'll go to high schools. I'm going to say high schools. Like throwing, like pencils at the guest, nerd.
No.
Are they that engaged?
Yeah.
Cool. Because when I get them, they're just like, oh gosh, don't, just be quiet, just give me the answers, give me the review and I'll get through it.
Who could react that way to fire though?
I know, well, I would love to come, so we have here. So we have the truck, we have the LiDAR, we will launch a weather balloon, we will come to any campus, and we will do this as a demonstration, and we'll do a little lecture on fire behavior and fire science at any level, 6 and up. So just, if you're interested in this content, I would love to get this content into the classroom as part of some sort of earth science thing. So that, actually, I forgot what this whole thing was about, but when I sat here and saw the introduction, I thought, oh my gosh, I don't have the right science, but this is perfect. So yeah, this is what I want to do. This is what we've done a few things, but we can do it. So there's all my contact information. And we actually are working, so I worked with Santa Clara Fire Safe Council to help develop this program, and they basically told me that 6th grade was the age where students generally get left home alone for the first time, they're getting able to come home alone, 6th, 7th grade, and they're more curious about fire. And that's why I was targeting 6th grade.
It's true.
Okay, so I don't know. But if high schoolers want this material, that's great. So I will adapt. And I haven't started it yet, so this is actually awesome. Yes?
To understand, we're moving into a project, real world style curriculum, adding math to science, so this is perfect for the new standards.
Okay. So,
Good luck.
And we're still doing modeling, so.
And modeling.
Okay.
Totally.
Modeling and math into standards. Yes.
okay. We have a pretty cool website. I don't know how I got this domain, but it's mine, fireweather.org. We post our data in real time there. There's a student of mine coded up a little script that takes a picture of our truck on Google Maps. So anytime we're on a fire, you can click on it and it gives us the real-time weather data, if we have a Wi-Fi connection. And you can follow us at Fire Weather Lab. We post data, we post images from wildfires and stuff, and so it may be somewhat interactive for students if they're interested in that. These are so most graduates, some are still lingering grad students that are finishing their thesis, so they are all responsible for this.
Do you work with what, Cal Fire?
Cal Fire, yeah, we actually put a weather station in Henrico State Park with them. We don't get funded by them, but we work with them.
Because you need to advise, give them advice or.
Well, yeah.
I know,
Yeah, I
I need
mean,
to come to.
The first time we got assigned to an incident was this summer. Usually we show up. We have state plates, we're all fire line qualified, we go anywhere we want. But we got called out by the fire weather meteorologist on the rough fire, which is where the Kings Canyon. And the team went there, and a lot of politics.
Yes.
And they were there for a day, they left. Press got kicked out a day later. National Geographic is doing a lot of work on these fires here in California, and they're trying to feature science and us They got kicked out, they got cameras like confiscated by the federal government, which is crazy. That